So today I want to talk about limits. And well, limits are interesting in itself, you know, and there are a few examples of limits that we'll use. And one of the examples is a product is one of the limits. And we actually start with a product. But mostly, I want to talk about limits because this is like the first example when you really have to stretch your mind in category theory, where you actually have to jump levels of abstraction. And this is so characteristic of all these reasonings in category theory. Because in category theory, everything is a category, right? I mean, we've seen as like, we have a category of sets, we have a category that has only one object, we have a monoid as a category, and then we have functors between categories, and gosh, these functors also form a category, right? With natural transformations as morphisms. And hey, categories also form a category, right? With functors as morphisms. So like everything is a category, right? So when you are jumping between levels of abstraction in category theory, you are just jumping from one category to another category, right? And at some point you are high in this category and you want to do some calculation, well, you have to descend a bunch of categories down to find out what you're really doing, right? To implement a morphism or something, or a natural transformation, you have to go down. So you have to, like, there's this ladder of abstractions, right? And it's easy to get lost. So I know it's late in the day, but I want you to really focus on where we are at a given moment. And I'll start slowly, and then we'll just like go into higher and higher abstractions, right? And this will be fun. So limits. I guess the starting point is going back to how we define the product, okay? Because product is like the best example for this kind of universal construction, right? So a product, I will remind you what a product is because you might have forgotten. It's been some time, right? So we have a product. We pick two objects in a category. So we have some category C, right? And I'm not going to draw the circle for the category, but we select two objects. We pick two objects, okay? Now mark my words. I'm saying select, pick these two objects, okay? We pick these two objects, and then we want to define an object. Let's call it little c, okay? Little c. That's their product, right? And we do this using universal construction. We are saying, okay, let's talk about candidates. What's a good candidate for a product? Well, a candidate for a product would be an object that has these two morphisms, P and Q, right? One goes from C to A and the other goes from C to B. And of course, there are many such possible candidates, you know? Like well, not every object in a category has two morphisms to A and B. But there might be lots of them, right? Potentially, I mean, in set, everything is connected to everything. In category set, for instance. So, lots and lots of candidates. And then we pick the best candidate, right? And I'll remind you how we pick the best candidate when we get to this point. But what I want to say is, this is a good starting point for generalization. And I'm going to show you how people generalize things in category theory. So first of all, they say, okay, so what do I mean by something I just said. Okay, what do I mean by selecting two objects? What does it mean to select objects? Huh? Like everybody knows what it means. You know, how do you pick objects? I mean, hunter-gatherers were picking berries, right? So we know what picking objects means, but how do we describe it in terms of category? Well, these two objects form a pattern, right? So how can we describe a pattern of two objects in category theory? Well, of course, as a category. Duh, right? So let's have this category that has just two objects, you know? Let's call them 1 and 2. And we'll call this category 2, like bold 2, let's say, okay? So we have a category with just two objects. And of course, if it's a category, it has to have what? Identity morphisms. It doesn't have to have anything else, but it has to have identity morphisms. So there have to be these two identity morphisms. But other than that, we don't need anything. Okay? So a category that doesn't have any morphisms other than identity morphisms, I don't know if you remember, it's called a discrete category. Right? So we have this discrete category with two objects, and this is our pattern. Right? But now we have this humongous category C, right? And we want to say, what does it mean to pick this pattern inside C? Okay. Well, so we have to pick two objects, right? So it's a functor, obviously, right? So any functor that we define from 2 to C, right? Let's call this functor D, okay? It will map object, so it will map object 1 to some A, and it will map object 2 to some B. And there we go, we have a selection of two objects. Every functor from 2 to C is equivalent to a selection, yes?
Do they have to be unique for the functor?
In what sense unique?
Can the functor map 1 and 2 to the same object?
Good question. Can this functor map A and B, map 1 and 2 to the same object? And yes, why not, right? Why not? And what does it mean, like in the case of product? Well, we want to define a square of A, right? A product of A with itself, right? For that we need a functor that maps both objects into the same object, right? So yeah, this is great. This is a great generalization. It covers all possible cases of interest, right? So there are lots of functors from this category to category C, right? And we just have one functor that picks these two objects A and B. So this is what picking means. Okay, now we understand, right? Our hunter-gatherer ancestors didn't realize that they were dealing with functors. Now what about this object C here? We are picking this candidate, right? So what does it mean, picking this candidate? How can we describe this? Okay, a category 1, are you saying? Yeah. Okay, so yeah, it would be natural to say, okay, so let's get a category with one object, and a functor from this category would pick one object C, right? And indeed, there is a construction that goes along these lines, and it's called a Kan extension, right? But we are not ready yet for this. But because it's much more general, okay? Kan extensions do much more stuff than limits. And today I want just to talk about limits. But Kan extensions are very interesting. So this line of reasoning would eventually lead us to Kan extensions. But for now, okay? For now I'm going to do this. I'm going to say, well, what about these these functors that map both to a single object, right? These are also functors, right? So there is a functor that will map both objects into the same object. Let's call this object C. And this functor is called delta C. Delta C, it's a constant functor, right? We've seen this functor before, and I said, okay, this will be important at some point, right? Don't forget about the constant functor. So the constant functor, delta C, maps every object into one object C. Every object in this category into one object C, right? And did I mention that functors also map morphisms, right? We remember that, right? So in this case, this is sort of a trivial thing, right? Because a functor has to map identity morphism to an identity morphism. So it will map this identity morphism into this, and this one into this identity morphism, and this one, both of these into this identity morphism. Fine, right? Right. So just to be sure that we understand, these are functors. They map objects and they lift morphisms, except that these morphisms are kind of trivial, right? Okay. So immediately, once I draw this picture, you might think there's an obvious generalization of this, right? Why am I picking this category here? What if I pick a different category? Right? That's my starting category. What if I have a category where there is a morphism from 1 to 2, and so on, okay? What if there's a very complex category here? So this line of reasoning, once we've established what picking means, that it means a functor from some kind of category we consider a pattern, right? Then we immediately open up this field of generalizations where this category can be an arbitrary category, right? So when we define limits, we'll make this general, and we have limits, okay? But let's stick, for the moment, let's stick to this. And the next thing was, we have two functors now, okay? Remember this thing called natural transformation? Okay, natural transformation between two functors. So if we have two functors, we can define a natural transformation. So let's define a natural transformation from this functor delta C to this functor D, right? This is the functor D. Okay, let's erase this. This functor is D, okay? It maps 2 into C. So what's a natural transformation? A natural transformation is a family of morphisms, right? So we look at these two functors. So in general, we have two categories. We pick an object here, let's say X, and it's mapped by first functor delta C, into delta C X, and by the second functor is mapped by using D into dx, let's say, something like this, right? So a natural transformation is a family of morphisms between these two guys. So we pick one morphism per object. So for object X, we pick this morphism, right? For every object in this category, we pick one morphism between its images, okay? So that was the definition of a natural transformation. A natural transformation is just family of these morphisms. We pick these morphisms, from this, between these images, right? And there was also a naturality condition, okay? But before we get to naturality condition, what would it mean to have a natural transformation between, so this is our delta C, and this is our D, between these two functors. Okay, so it's a family of morphisms. Well, there aren't that many morphisms in this family because there are only two objects to start with. So there's one morphism for 1 and another morphism for 2, right? So let's look at 1, okay? Delta C maps it to C, okay? D maps it to A. So it will be a morphism between C and A. Okay. So that's one component of our natural transformation. Let's call this natural transformation alpha, let's say. Alpha C, that will be this, right? Second component, object 2. Delta C maps it, again to C, okay. D maps it to B. Okay, so a natural transformation will be, a component of natural transformation will be a morphism from C to B. So this will be alpha, this is alpha 1. This is alpha 2, right? They are indexed by the object in the source category. So this is alpha 1 corresponding to object 1, alpha 2 corresponding to object 2. Okay? Now, in this case, that's it. We don't really have to worry about naturality condition because naturality condition comes into play when there are morphisms that have to be mapped. In this case, the only morphisms we have are the identity morphisms, and they always work out. So there's no worry about that, right? So we don't have to impose any additional naturality conditions. That's just it. Okay? Now, you might recognize I have just redrawn this picture, right? So a natural transformation between these two functors is really this diagram. That's it. We've got this diagram. Now what happens, so now that we have this, right? Let's go generalizing. Right? Let's say, let's pick a more interesting category. Let's call this category, let's call it the index category, I. So here we have a category that we call I, and it has a bunch of objects, and it has a bunch of morphisms, okay? Something like that. Now, there is we define a functor, again call it D, and it will pick objects from this category, right? So this will be, let's say, let's call this object I. This will be Di. Okay, I, J, K. This is Dj, this is Dk, and so on, right? It also maps morphisms now, right? The functor maps objects to objects and morphisms to morphisms, right? So it will map these morphisms. So this is if this is an F, morphism F, then this will be DF. And of course, as before, you might ask me, is it okay if I shrink it? It's like maybe all of them will be shrunk to a single object and so on. Yeah, it's fine, right? So we have this functor now, D, and now the name D actually comes from diagram because this sort of creates a diagram in this category, right? So this is a pattern that defines sort of like a graph, right? A diagram. It embeds it here. So this functor embeds a diagram. It's a diagram functor. Okay? Now, as before, we will have this delta C. Same thing. Okay, so it maps the whole thing into one object C and maps all of these morphisms, including identity morphisms, which I don't draw anymore because I'm too lazy. Right? All these morphisms are mapped into a single identity morphism. That's the definition of delta, right? Before we didn't have any additional morphisms, so we didn't care. But now we have all these morphisms. So F is mapped into ID. This guy is mapped into ID. This guy is mapped into ID. All of them are mapped into ID, by definition of delta. Okay? So now we can define again this kind of construction as using natural transformation. So what's a natural transformation between delta C and D? Well, it will be a family of morphisms again, right? Let me use the red marker, right? So for I, we'll connect C, because I is mapped to C using delta C, to DI. So we'll get this guy, right? And for K, we'll get this guy. For J, we'll get this guy, right? So they form sort of like a pyramid, right? And it's actually called a cone in the category speak. And you can imagine that, you know, it's like if you have lots of objects here, then it's sort of like you draw a circle, and this is the apex of the cone. So this is a cone, this is the apex of the cone. So a natural transformation is just this bunch of morphisms, right? However, now that we have morphisms in our initial category, we have to worry about naturality conditions, right? And I will remind you what naturality condition is. Naturality condition says that, okay, so if we have one object X, that's great, but we want to see what happens when we have a morphism F here, right? So a morphism will go from some X to some Y. And now Y, again, is mapped in two ways. Okay, I don't know where to draw this. Okay. So this is, let's say the first functor is delta C. So this is delta C acting on Y, and this is D acting on Y. Okay? So this morphism F, okay, I've drawn it in red. So this will be our. So morphism F goes from X to Y, so it will be mapped to something that goes from delta X to delta Y. So this is our delta CF. Well, okay, delta C actually maps both to the same point, right? So delta CF is really identity. But in general, if this were a different functor, it would be different, guys, right? Now, D maps F to a morphism DF that goes between dx and dy. So this is just functor part. Every functor maps a morphism to a morphism. This is what in Haskell we call fmap, right? You take this function and you fmap it, and it goes between the images of the functor, right? So these are the fmap parts. But now we have also a natural transformation, and a natural transformation, its component at x connects these two guys. So this is alpha at x, right? So x is mapped by one functor to this, by the other functor to this. And the natural transformation goes between these two images. And its component at y maps delta cy to dy. So naturality condition just says we want these two paths to give me the same result. So this alpha y after this should be the same as df after alpha x, right? So that's naturality condition. This thing must commute. Now, because this guy is an ID, right? These two guys are shrunk. What it means is that this triangle has to commute, right? So if we shrink this to a single point C, right? Because delta C maps everything into a single point C, then this square becomes a triangle. This shrinks to a point, right? So alpha x df after alpha x must be the same as alpha y. Okay? So that means all these triangles here have to commute. That's the naturality condition. So that's the definition of a cone in a more general setting. For arbitrary index category, we create this thing. We have a functor d, and we use the functor delta c, and the natural transformation between these two functors is called a cone, right? And a cone is just this bunch of morphisms here that make these triangles commute. In the case of product, we didn't have the bottom didn't have any morphisms, so the triangles there were no triangles to commute. But in general, these triangles have to commute, right? So now let's talk about the universal construction. This is just a definition of a single cone, right? Or a single pattern like this. Now what we had when defining a product, we had lots of these potential products, right? Lots of these C's here. So in this case, it would mean we have to have lots of cones, right? Lots and lots of them, right? Potentially. And we have to pick the best one. Okay. So what was this thing about picking the best one? Picking the best one out of these meant that the best guy, the actual product, A cross B, with two projections which we call first and second, right, has this property that for any other candidate there is a unique morphism M from C to A cross B, right? So M goes from C to A cross B, our good guy, right? The universal guy, right? Such that these triangles commute. So we have the condition that first after M must be equal to P, and second after M must be equal to Q, which we said that kind of looks like factorizing numbers, right? These two numbers have a common factor M, right? First times M equals P, and second times M equals Q. So this is a factorization. We are factorizing these projections. But the important thing is that, you know, first of all, two things important. Unique morphism, right? That this morphism M has to be unique. There cannot be two morphisms that factorize these cones, triangles, right? And there's this commutativity thing. So how do we translate it to this picture? Well, so we have cones now instead of this simple diagram. So we'll have, like we have this cone And we want to have a universal cone. So a universal cone would be, and this universal cone is called the limit, okay? Well, the limit really is the whole cone, but in most cases we just say that this object is the limit, right? But we understand that this object plus all these projections, let's call these projections, right? So this will be called the lim D. It's a limit of this functor D. So for every D, the limit will be different, right? So for every pair of objects, the product is different. So we have this cone, which also has these projections, and all these little triangles commute, right? But now, the universal cone has this property that from any other apex, from any other cone, there is a unique morphism M. Okay? So you see how we are going abstraction levels up and up and up, but these are small steps, right? So we are saying, okay, here it was a simple thing, just A and B. Here it's a more complex, it's a diagram. Now we are adding on top of this, we are adding this commutativity, right? So now we have more projections, not just one projection, right? And these projections have to form these commuting triangles. Now we have two cones, right, instead of just two of these triangles. And we said something about these triangles commuting, okay? So what's the corresponding thing in here, okay? So now concentrate. What corresponds to this triangle? Okay, do I need like an additional color maybe? I don't know. Let me use black for this. So these triangles were formed. One side of the triangle was the M, right? Okay, so M is this guy here. The other side of the triangle was a projection from C to one of the, so from the vertex of one of the cones to some object B, right? So we'll pick this one, okay? So from C, let's say this one, okay? This guy, okay? And the other one was from the limit. Here it was the product, right? So this guy to the same guy, right? So it has to be from lim, from product to this B, and this is like our B, okay? Okay, so I'm doing little steps, right? It's like, okay, what is the triangle here? What would be a corresponding triangle here, right? So the corresponding triangle is this, okay? So this triangle has to commute, right? And there are many triangles like this. All triangles that have M as its, let's say, height, right? All these triangles that have M as its height, they have to commute. So there are three triangles here. This one, and this one. They have to commute, okay? Now we are back to commuting triangles. So we got rid of some commuting triangles by saying there is a natural transformation, that the cone is a natural transformation, right? But now we have these other commuting triangles. So this is a standard trick in category theory. Whenever you have commuting triangles or commuting squares, you try to replace them with a naturality condition. So we have to find two functors and find a natural transformation between them, and such that the naturality condition for this transformation makes our triangles commute. But for that, we need to go a little higher in our abstraction ladder. We have to objectify cones. So we make cones objects. So for every cone, we have a unique morphism going from this cone to the limiting cone. Okay? So the question is, do you remember something that I said before, like from everything, every something, there is a unique morphism to this thing. That was the definition of the terminal object in a category, right? So this is the kind of categorical thinking, you know, it's like, I've heard something that sounded kind of similar. Oh, okay. So one thing is, it sounded similar. The other thing is, wait a moment, everything is a category, right? And we started with this. Everything is a category. Well, don't cones form a category? Wait a moment. Maybe cones form a category. I mean, what's a big deal with a category, right? To define a category, you just have to define what the objects are. In this case, cones, okay? And morphisms. Okay, so what would be a morphism between two cones? A morphism between two cones would be a morphism between these apexes, right? Or apices.
Apices.
Apices, huh? I guess. So, okay. So we can define a category of cones based on this category, based on these two categories, right? Based on this whole picture, right? We're just picking things from this picture and saying, this is an object. Okay. So an object in our new category corresponds to a cone in the old category, and a morphism in the new category corresponds to a morphism between apices, between these cones. Okay? All right. Now, of course, you would have to say, okay, for this to form a category, first of all, is the identity morphism defined? Yeah, a morphism between two, an identity morphism of the apex, right, connects two cones, and it's a good morphism, right? Oh, but we want these morphisms between cones to actually be special morphisms. So not every morphism between these two apices is good. A good morphism between apices is the one that has these commuting walls, okay? So this commutation condition, we will say that there is a morphism between two cones only if there is a morphism M that makes these walls commute, these triangles commute, okay? So this is a very special category. This is a category in which cones are objects, and morphisms are these special morphisms between apices that makes these things commute, okay? And it's just a fancy way of saying, hey, you know, they form a category, right? And of course you would have to prove that if you have, you know, two such morphisms that their combination, right, composition, also is a good morphism. So in this case, of course, two morphisms will compose to create another morphism, but is that morphism also making these walls commute? And if you draw these diagrams, you immediately see that, yeah, of course it makes these walls commute, because it's like this triangle, blah, blah, blah. If these two triangles commute, then the bottom triangle commutes, and everything commutes, right? So it's fine, so it's a category. So the terminal object in this category is this cone that has a good morphism coming from every other cone, right? And this is the cone that we call the limit. Okay? So we have reused some ideas from category theory, the earlier ideas that how to form a category and an idea what a terminal object is, and we have reused it to define a limit. Okay, cool. So now we know how to define a limit. But let's think a little bit more about this. So, like what's a cone again? Oh, a cone is a natural transformation. So this is really, this cone here, that's really a natural transformation from delta C to D, right? Okay, and we say, that for every cone, for every natural transformation, just the translation, right? Every cone, every natural transformation, there is a unique morphism. Okay, so these cones form a set, and this is another clever trick in category theory. Instead of talking about elements, let's talk about the whole set. Okay? So cones form a set like this. Set of natural transformations. This is a set of natural transformations. Every element of the set is a natural transformation. For every element of this set of natural transformations, meaning for every cone, we have a unique morphism. So a morphisms also form sets, remember? Because these are called Hom sets. Hey, so this is a Hom set in the category of C, going from object C to this object that we call lim D. Right? And what's even better, this is a unique morphism. For every point here, we have every element of this, there's a single element in this. So it's a nice mapping. And in fact, this is a mapping that goes both ways. Because if we have a morphism like this between some cone, whatever cone, and the limiting cone, right? If we have this morphism, then we automatically have a natural transformation going from delta C to D. How come? Did you see that? Like I'm giving you this morphism here. And I'm giving you this cone, right? How do I create this cone? Well, okay, so this guy will be this guy after this, okay? So I'm just constructing this new cone by saying this line here is this followed by this. This one followed by this, right? So I'm just closing these triangles. I have M, I have this cone. I can create this cone by closing these triangles. And they are automatically commuting because I've formed them this way, right? So I have this part of the cone, the M, right? And I have this part of the cone, this guy. So I get this guy to close the triangle. So there is a one-to-one correspondence. This is not just one way. There is a one-to-one correspondence between these things. So I have a one-to-one correspondence between natural transformations of this form and Hom sets. Now look what happens when I try to vary C, because this is like a single, cones based on a single C here. And these are morphisms from between just this point C and lim D. What if I vary C? Because I want to take into account all possible cones, not just the ones that are coming from C, right? There could be many cones coming from the same vertex, from the same apex, right? There could be many different natural transformations. They're all natural. But I really want to vary C around. So if I vary C, I get something that is a mapping from C to natural transformation and from C to a Helm set. Okay? This mapping and this mapping. Okay? That's an object in category C, and this is a set of natural transformation. This is an object in category C. This is a set of morphisms. A set is an element of the category set. A set is an element of the category set, right? So these two guys are both mappings from category C to category set. See that? And I bet they are functors. Huh? These mappings between categories, they better be functors. Now, indeed they are, okay? However, they are contravariant functors. I don't know if you remember still, there were covariant functors and contravariant functors. When you vary the first argument in the Helm set, you get a contravariant functor. And the same thing here, right? So, I think probably it's a good point to stop, because your heads are probably exploding right now, right? So I got through, this is getting through these levels of abstractions, right? Like you go higher and higher. So you have a set, oh, you have a functor, and now you have two functors. And there's this thing between these two functors, right? So first of all, I have to show to you that these are contravariant functors, right? And I'll do this next time. I'll show that this is a contravariant functor. That's easy to show. This is a little bit more difficult. Like, is this really a contravariant functor? How do I show this, right? And now if I show you that these both are functors, then if you have a mapping between functors, well, it should be a natural transformation, right? Yeah, I mean, it would be nice if it. Indeed, you can make it a natural transformation, and then the naturality condition for this natural transformation, this guy will give you these commuting triangles. So I will have a setup in which I can get rid of these commuting conditions. I'll just say, well, it's a natural transformation between these two functors. What's there to prove, right? Okay? So this will be really exciting next time. Thank you.